All right, next up, so complex numbers are just point in the plane. It's just different notation. So if you have the point AB or the vector AB, you can write it as A plus BI using the complex numbers notation. So Z is equal to A plus BI. But we want to do more, right? So when you have like two complex numbers, you can add them up or subtract them, just like you add or subtract two vectors in R2. But what about multiplication and division, things that we can do with real numbers? Can we do the same thing with complex numbers, which we cannot with vectors? And the answer is yes. But to get there, we need to talk about complex numbers using a different point of view, and that's the polar form of a complex number. So this is what this section is going to be all about, how to write a complex number in polar form. So to get there, we need two definitions. The first one is the modulus of a complex number, or also called the absolute value of a complex number. So if you start with a complex number, Z is equal to A plus BI, the absolute value of Z, so we're using the same notation as absolute value, is simply the distance between the point P at the location AB and the origin. So if you have a complex number is A plus BI, so we have Z here, so the X coordinate is A, the Y coordinate is B, so the absolute value is just the distance between the origin and the point Z. And of course we're using the absolute value notation because the absolute value for real numbers is measuring the distance between that point and the origin. Like, what's the absolute value of -1? Well, it's 1 because it's 1 unit away from the origin, and that's the origin story of the absolute value for real numbers. But now we can do this for complex numbers. And of course, if you want to compute that distance, well, you can see that every complex numbers, except maybe complex number at the origin, you can construct a right triangle where the base of that right triangle is going to be given by the real part A, and the height of that right triangle is going to be given by the imaginary part B. So if you use Pythagoras' theorem, A squared plus B squared square rooted is going to give you the length of your hypotenuse. So the hypotenuse here is the same as the distance between the origin and the complex numbers A plus BI. And this is how you get the absolute value of a complex number. The next definition that we need to create a polar form of a complex number is the argument of a complex number. So the argument of a complex number, so here the complex number cannot be 0, so 0 cannot have an argument. And it's very similar to some extent when you're talking about direction of a vector. You cannot talk about direction if your vector is 0, so same thing here, there's only arguments for complex numbers that are not the 0 number. So normally we use phi for the argument or argz for the argument of the point Z. So this is simply an angle, and this is the angle between the positive side of the real axis and the line segment that's joining the origin and your point Z. So here I draw this thing in green, so this is your argument phi. So that angle is typically an angle between -180 and 80, so minus pi to pi if you're using a radian, and here you just have to make sure that you read your question. Sometimes we use phi to be an angle between 0 and 360. Really, at the end of the day, it does not really matter if in some book they use minus pi over 2 or 3 pi over 2, because these two angles are coterminal. You're going to be able to know where your complex number is. So anyways, just read your question, see where the argument is specified. I like between minus pi and pi, and in most of my examples will use that. But I think most examples online, they use an argument between 0 and 2 pi. So just read your question and answer accordingly. Anyways, this is based on geometry of right triangles that you should be fairly familiar with. And now here, and this is the most important part, is that you can use the absolute value of a complex numbers and its argument to rewrite that complex number in polar form. So in order to do that, what do? So we look at our complex number, a plus bi. This is called the Cartesian form of your complex number. And we want to locate that point on the Cartesian plane, but using two things, using like how far this complex number is from the origin, and then at which angle. So you cannot just use one of those two numbers, because if you say, hey, I have a complex number that is like at 3 units away from the origin, well, if you just say 3 units away from the origin, you're going to create like a circle of radius 3, and you don't know where on that circle you're going to be. But if you say, hey, I'm 3 units away from the origin at an angle of 40 degrees, well, then there's only one point on that circle of radius 3 that is at 40 degrees. So with a distance and an angle, you can locate uniquely a point on the Cartesian plane. And this idea of using the distance and the angle is called the polar form of a complex number. So geometrically speaking, because we have a right triangle here, we can work with it. So for example, and I wrote this as a remark, if you compute cos of phi, so that's the adjacent side, so the adjacent side here is a divided by the hypotenuse, which is the absolute value of z. So a over z is going to be cos phi. So if you isolate a, you can see that a is going to be equal to the absolute value of z times cos of phi. So we're rewriting a, which is like the x coordinate of that complex number, as a formula that only depends on the absolute value and the argument. And same thing now if you use sine of phi, so that's the opposite side, which is b, divided by the hypotenuse, which is the absolute value of z. And then if you isolate b in that formula, you get that b is equal to the modulus of z times sine of the argument. So you can now look at your, and this is what I did here in my remark, you can start with your complex number z is equal to a plus bi, and now you replace a by z cos phi, and you replace b by z sine phi, and now a and b are gone. We have a brand new expression that only depends on the absolute value and the argument. You can see here that the absolute value appears on both terms, so you can factor out the absolute value of z and put it up front, leaving behind cos phi sine phi, and that part here. So just to make it more cute, we put the I before the sign here, just because it's easier to read. But when you are putting the absolute value of z first, then bracket cos of phi plus I sine of phi, that's called the polar form of your complex number. So Cartesian form, so that's the Cartesian form, a plus bi, which depends on x and y, and then there's the polar form, which depends on how far is it from the origin and at which angle is it from the positive side of the real axis. Let's do some examples to illustrate this concept more clearly. So let's do some examples. So we want to compute the polar form of some complex numbers. So the first one we have here is the complex number I. So what is the polar form of I? So what you need, as usual, is first you need to compute how far the complex number I is from the origin. And of course here, this complex number is 1 unit away from the origin. I mean, this is by definition. So it's 1 unit away. And what about the argument? Well, the argument is 90 degrees. So the number I is at a 90-degree angle. So the two quantities that you need to write the polar form of I is, well, it's 1 unit away from the origin at an argument of 90 degrees. So when you're constructing the polar form, so you write the absolute value, so it's 1 unit. You write the argument, which is pi over 2 or 90 degrees, and then the polar form, you write the distance first. So even if it's a 1, you write the 1 here. So the polar form, it needs to be clear. I see how far is it from the origin as the first coefficient, and then I write my arguments inside my cosine and my sine. So the polar form for I is 1 times open bracket cos pi over 2 plus I sine of pi over 2. Let's do some other examples. So for example, what's the polar form of minus 2i? First, you need to compute how far is it from the origin. Well, it's 2 units away from the origin. And then the angle, you could choose minus pi over 2. So minus pi over 2 would work. Or if in this example, I'm going to use angles between 0 and 2 pi. So you can also use 3 pi over 2. So minus 2i is 2 units away from the origin with an argument of 3 pi over 2 or 270 degrees. So the polar form is 2 open bracket cos of 3 pi over 2 plus I sine of 3 pi over 2. And that's the polar form for that one. Next up, we have minus 1, another important example here. So minus 1 in polar form is, well, it's 1 unit away from the origin. And now the angle of minus 1 from the positive side of the real axis, well, the angle is going to be simply 180 or pi. So for minus 1, it's 1 unit away from the origin at an angle of pi. So the polar form is going to be 1 open bracket cos of pi plus I sine of pi. That's minus 1 in polar form. What about 3? Well, for 3, well, we know 3 is 3 units away from the origin, and because 3 is a strictly positive number, the argument is 0. So the polar form for 3, well, absolute value is 3, argument is 0. So the polar form, it's a bit creepy, but this is the answer for 3. It's 3 open bracket cos of 0 plus I sine of 0, and that's the polar form for 3. So the polar form is not something compact, it's kind of ugly, but it really reflects the geometric nature of how to position these numbers on the Cartesian plane using how far away they are, using the absolute value, and the argument, so the angle from the positive side of the real axis. And then for the last 4 example, 1 plus I minus 1 plus I, so 1 plus I minus 1 plus I minus 1 minus I, or 1 minus I. First thing you can realize is that all these arguments, all these complex numbers, they are inside a right triangle where the base and the height is 1. So the distance between these points and the origin are all root of 2. So all the absolute value of these 4 complex numbers are root 2. What about the angle? Well, for the first one, 1 plus I, you can see that the angle is simply 45 degrees, so pi over 4. For minus 1 plus I, well, you're at 3 pi over 4. So if you go from the beginning here, so 3 pi over 4. If you are looking at the argument for minus 1 minus I, you're going to be at 3, 4, 5 pi over 4. And then finally for 1 minus I, you're just going to go all the way up to 7 pi over 4. So the arguments, so the polar form for all these complex numbers, so all the absolute values for all 4 are root of 2. The arguments, it goes from 45 degrees to 135 to 5 pi over 4 and then 7 pi over 4. So they're corresponding polar forms. So for the first one, I'm just going to read the first one. So root 2 open bracket cos of pi over 4 plus I sine of pi over 4. And then it's the same thing for the other one. So you see I use the absolute value first, and their corresponding arguments, and those are the polar form for these other complex numbers. So in this section, the focus is to understand that you can start with the Cartesian form of a complex number, which is solely based on the x and y position, or you can use the polar form, which is another way to locate a point in the Cartesian plane using 2 other numbers, how far away they are from the origin and at which angle from the positive side of the real axis to the line segment that links that point to the origin. And that's it. And we need this because this is the key concept that will allow us to define the geometric origin of complex multiplication and then complex division. Without the polar form, there's no geometric background for those operations. So this is something new for complex numbers only.